Okay, ladies and gentlemen, I'm excited to start this short course today. It combines two different topics that are both of them very interesting. One is deep learning, of course, and the second one is cloud and edge computing. There are people that have expertise on either of these fields, but there are very few people that have expertise on both. So if you attend this course, you will be able to do decentralized or federated learning, for example, using tools that come out of cloud and edge computing. And I'm going to attend myself this course as well, because though I know many things about deep learning, I don't know many things about cloud and edge computing. So it's going to be good for me as well. So I would like to thank Lorenzo Carnevale from University of Messina for volunteering to give the first three lectures. And I would like also to thank the TEMA partners. TEMA is a project that is on big data analytics for natural disaster management. It organized this short course, and it's delivered in the framework of the International AI Doctoral Academy. So now, Lorenzo, the floor is yours. We cannot hear you.
You hear me now?
Yes, sure.
Okay. Yeah, I say thank you, Professor Peters, and again, good morning to everybody. I'm assistant professor at the University of Messina, and my research activity is at the cross of cloud, edge computing, and artificial intelligence. This is why, Professor Peter mentioned also the application of federated learning, which is one of the most important at the cross of the two fields right now. So the free courses are about cloud and edge computing in general. So a really brief introduction. I will try to don't be so long. So I will try to adapt the lecture according to the time we have. Then I prepared something about microservices, so containers and Docker containers, specifically the technology that enables us to work with containers. I have also some slides with some hands-on. I don't think we will have time to do something command line, but there will be in the afternoon the practical session where part of this will be shown, and then the same thing for Kubernetes, which is the orchestrator of containers. Let me now share the screen. So I will share my entire screen. Okay, may you see the screen?
Yes, perfect.
Okay, I'm going full screen. Okay.
Connect to smartphone.
Okay. Well, let's start by discussing about cloud computing and mostly why cloud computing. If I understood well, the community to which I'm discussing is probably more used to discuss about artificial intelligence, machine learning, and deep learning. As you know, the trend that we have now is the trend of large language models, and this kind of trend is here since years. Large language models were not, created 2 years ago by OpenAI, but OpenAI, had really the smart idea to put this kind of models and then the artificial intelligence on a cloud platform. In this way, they created ChatGPT. And ChatGPT is just a software as a service platform. We will see what these terms means, that enabled everybody around the world to access this kind of knowledges and intelligence. And this become really pervasive. I don't know in other country, but in Italy, at the beginning, deep learning was discussed in radio. So really in a mainstream channel, and it was really surprising to me. But really, the great advantage that OpenAI got from the creation of the model was putting the model into something like the cloud computing. Let me now, discussing about cloud, and then we will see what the edge computing is and what is the relation with between. So cloud computing, of course, is a terms with which we specify services and development of services over the internet. Services are hosted in remote infrastructure, in computers or better data centers that are geographically dislocated all around the world. The services become ubiquitous. We can access them from anywhere and with any device. We can access it from the computer here in a desktop station, or we can access them from the smartphone. I created the slides, and my colleagues helped me to create the slides using a cloud platform, the platform provided by Microsoft, no, the Office 365. The result at the end is like about commodity, like utility is called computing model, which is like the utilities we have every day at home, like the gas, like the electricity. And the great model that was behind is that we just pay for what we consume, for what we need, like we do, with the gas and with the electricity. Cloud computing, is of course a complex platform, which anyway makes transparent the underlying infrastructure to users and to applications by using some user interface or some APIs, so the application programming interface. Then this platform, as I said, is provided on demand, anywhere, anytime, from any place, and the software services are available for enterprises, general public, corporation, business markets, and so on. This is a kind of general infrastructure of cloud computing, where there is a shared pool of computing resources. When I talk about computing resources, I have to mention CPUs, memory RAM, disk, so storage, databases, networking, and all of them are on demand used by the user. The user doesn't ask really for resources, but just asks for some service. And the cloud computing behind tries to better assign the needed resources according to the ones required by that service. And that's why, we have some kind of service provider that tries to broaden this kind of approach. Cloud has specific characteristics like flexibility and elasticity, because the resources can be elastically grow when they are needed. Resources that again could be about CPU. So that means if our application needs one or two cores of a CPU, this will elastically assign to these services one or more of these CPUs. The same for the storage. So if our application is using 1 GB of storage for a computation, but after some then the computation will require for more space, this will elastically be assigned to this service. So at the end of the day, the user and then who uses this kind of services pay just for what they use, and that means the resources are always on, anywhere in any place. Just the user asks for the utilization of such resources. So the cloud is transparent and can be built in multiple ways. So there are, of course, different big players in the field of cloud computing, but also small players that try to provide cloud computing facilities. So that means these providers could be proprietary of hardware or software. The software could be open source or not. The products could be branded or not. In general, I mean, they are built like a cluster of personal computer servers or just, I mean, data centers that are dislocated all around the world in a, let's say, anyway, complex infrastructure. These are the layers of cloud computing that more than 20 years ago now were theorized and on which, I mean, the cloud computing is built. From the bottom, we have the infrastructure as a service, which is most related with the engineer, network architects, who installs the hardware, no, the bare metals. Then we have the platform as a service. We will see them in details in a while, but just to have a brief overview. The platform as a service is the layer of the cloud computing dedicated to applications and development. And then we have the software as a service, but we have really the end users. And some example that probably we use almost all of us every day is the email client like Gmail or Microsoft Outlook. I mean, these are described like this. I mean, we can see that in the software as a service provider application, that provider only provides software as a service while the cloud infrastructure is provided by another provider, which is the provider of the cloud infrastructure. And we will see, I mean, what is in the management of this kind of providers for each of the layers. So, for instance, an infrastructure as a service provider only provides infrastructure as a service, so really the hardware. The infrastructure as a service then is the delivery of really a technology infrastructure, and the provider of the infrastructure as a service manages the scalability of the system. Usually, the utilization of this infrastructure is built on the usage, and the software over this infrastructure is virtualized. So it's built over a virtualization layer. With the virtualization layer, we can logically create multiple computers inside one single computer, which is really a winning approach, because we created isolated logic machines inside one single machine that, from the security point of view, but also from the utilization point of view, is quite strong. So that's why, I mean, they provide a pool of virtual machines that are connected in internet, in a private or in a public internet, and then they have the virtual network devices. So the virtualization, as I said, was the winning approach for the infrastructure as a service, because then we have a layer of abstraction of the underlying infrastructure. With the classic virtualization, which is different compared with the containers, we will see them later. In the classic virtualization approach, we virtualize an entire stack of technologies, and we virtualize also the hardware. So the hardware is like recreated from the software point of view, and the user of that virtual machine doesn't have an idea to be inside a virtual machine. For the user of that virtual machine, this is the entire computer. So it's an abstraction of the physical host machine that is underlying. There is a specific piece of software which is called the hypervisor. The hypervisor intercepts and emulates the instruction from the virtual machine to the operative system which is underlying. The virtual machine is typically called guest because it's a guest inside the operative system, and the operating system that runs virtual machine is called host. There are multiple hypervisors. The most famous and not open source, so commercial one, and VMware, for instance. There is also Xen. Xen has also some open source solution, and then we have also VirtualBox, which is one of the most common used also for education. The hypervisor, of course, provides infrastructure APIs. VirtualBox, for instance, has a user interface that facilitates the running of a virtual machine and the management of a virtual machine, but there is also a command line. So it's possible to use and to manage virtual machine in a headless approach. Infrastructure as a service took also different names because there is anyway the trend to have like a XaaS, so like a job, with the X we can put any kind of name, because at the end we can have a computing as a service, the storage as a service, database as a service. So the concept of as a service becomes a billing model in cloud computing, and what the cloud provider provides depends just on what they want to do from the business point of view. Examples of infrastructure as a service, of course, are provided by Amazon, but there is also Microsoft Azure or Google Cloud Platform, which is also the unique one that provides the tensor process units or the other players are Rackspace, OpenStack. I mean, all these providers were really great, mostly at the beginning of the cloud era. It was more or less in 2008. And then, of course, the big players took the stage, and then they are kind of monopolizing the entire. The platform as a service provides instead facilities to support the life cycle of building and delivering application. This is mostly a tool used by developers. So the developer has a set of tools that helps him to build new applications. Let's imagine a Visual Studio Code provided on a cloud platform, for instance. So the compiler is there, the interpreter of Python could be there, the libraries could be there, the debugger could be there, and then just and of course also the underlying infrastructure. And so that means that the developer can just use these applications over a browser. Google Colab, just to make an example, concrete that maybe you use during your work activity, is a platform as a service. There is behind a set of libraries that typically is a Jupyter-like set, so Pandas, NumPy, TensorFlow, PyTorch, they are there available. You don't need to install them. Behind there is also a infrastructure which is really powerful, but this is provided for free. If there is the need to have, for instance, a GPU for the training, Google in the Colab notebook asks for some money. And then this is the pay-per-use model. So we use the GPU for instance, 1 hour of training, and then we pay just for this 1 hour. Even for the platform as a service, this could be a multi-tenant environment. So there are multiple domains and users that can access the infrastructure. And the infrastructure is highly scalable according to a multi-tier architecture. And finally, the model is completed with the software as a service, which is really a software deployment model, where the application is hosted as a service, and this is just used. Typically, the user cannot modify the application, but only some setting. Let's imagine, the Google Gmail. We can just access the software, so we can access our email client, and we can just tune some parameters in the settings. So we can change our signature, we can create folders, but we cannot modify the application. Of course, the software as a service behind has some infrastructure as a service provided by the software as a service provided, where this software is running. Software as a service is different. It's not a web application, because a web application is something that doesn't have behind a highly scalable approach, doesn't have the logic of elasticity, doesn't have the logic of on-demand services. Okay, so Software as a service is something that is not completely different, because anyway, there is a web application behind, but there is also the logic of some scalable approach. And mostly is also provided to be in a multi-tenant fashion. Of course, I mean, the cloud computing has different benefits and also disadvantages. Cloud computing enabled companies and applications, I mean, to be independent from the infrastructure. Before of the cloud computing, any organization or enterprise had to buy the parameters, had to buy the server, install them in some place in the office. That means adding also a good air conditioner system, because data center generates, I mean, generates warm. It needs to be refrigerated. Then the data center needed to be maintained. So with the cloud computing, all of this is going in outsourcing. So there is a cloud provider that provides this hardware on demand. The only thing that the clients at that point need is a desktop PC, a laptop, I mean, just a device with a good internet connection to access the cloud facilities. Applications then move on the cloud, and that means that they can just process and manipulate data, for instance, inside the cloud platform. Consider also that if during the time the data center needed to be extended with multiple, with different resources, they needed to be buy and install the data center. Now we have just to rent with the pay-per-use model directly from the cloud provider. So the consumer typically signs a contract to use the service. This is something we do also with Gmail, for instance, when we create the Google account. It's in the agreement that we typically skip, but is there inside. So the consumer pays then for what is used. There are, of course, facilities that are provided for free, like again Gmail, even if, I mean, we accept that Google uses our data, like payment. And then, I mean, a bill is provided after, I mean, the end of the cycle. That could be the end of the processment, or, I mean, on a monthly basis. So cloud computing provided several opportunities, like using an economy of scale. The cost is calculated on demand. Vendor and service providers claims the cost by establishing an ongoing revenue stream. Data services are stored remotely and accessible by anywhere. Let's think about Dropbox, iCloud, Google Drive. I mean, we store our data there inside, and then from anywhere with any device, we can just access them. The computing cost is lowered thanks to the cloud computing. We don't really need an high-powered or high-priced computer to run a cloud computing web application. I mean, our smartphones, since the beginning, were able to run software as a service. What we just need, I mean, is to have good internet connection in order to use such application. So the point is that we can also buy, I mean, a client which is not, I mean, so powerful. We don't need any CD, we don't need any DVD drive. And also the evolution of our hardware, so our laptop today doesn't have anymore a DVD drive, just because, I mean, cloud, I mean, changed completely the approach also on the TV. We improve also the performance at that point, because, I mean, we can use these resources elastically that are remotely located. Also, the cost of the software is reduced. Before, we had to buy like desktop application and to install in our in our system, in our operating system. Today, instead, we have free or softwares that are under the payment of a fee, like the Google Docs suite. That was really also a different change of paradigm in this approach. So, typically, if we want to use them for free, Google provides a way to have a word processor or a calculated processor like Excel. The software updates. It was another great advantage. We are never aware that there is an update. Really. Gmail updates, on a regular basis, but we don't see an update. We don't we don't leave a discontinuity of the service. Different is if we have to maintain our data center and then we have to update, for instance, the underlying operating system. The data server needs to be switched off. Otherwise, we cannot really do it. So we need to migrate all the data on another computer, then doing the update of the software, and then probably bringing back data where in the original place. This is something that is already done, is anyway done by the cloud computing provider. But given that they have many facilities, many hardware available, this is quite transparent to us, and it happens in a way where we don't have any disconnection. Also, the possibilities to have document format compatibility. It seems, not so important, but if you remember, we had at the beginning some issue using, for instance, a word processor in Mac or in a Windows system. They were not compatible. But with this approach where the files are accessible from anywhere and from any device, this pushed a lot the software creators on making compatibilities between the different hosts. The document so can be universally accessed. We can also share this document between our colleagues, or we can also try to have an history of the document. We can then retrieve a previous version of that document because we see that we made an error, so we want to get back. And the latest version of the softwares provided by a cloud computing provider are always available. So the cloud computing always hosts the latest version of the document. So as long as I'm connected, I can have the last version of my document. Storage capacity could be, ideally unlimited, because cloud computing offers virtually limitless storage. Of course, we pay for having more, but there are already providers like Google Drive that provides 15 gigabytes for free. But just with the 20 euros per year, just to make an example, this is extended to 100 or 200 gigabytes, I don't remember. In our university, for instance, we have an agreement with Microsoft Azure, and per person, so per each account, we have something like 5 terabytes. Okay, so this is really a huge amount of space for a single person. And if we think that it was quite impossible today to have a disk of 5 terabytes in our laptop, just because it makes things really expensive. So our computer with a 5 terabyte disk could be really expensive. Cloud computing provided us, the possibility to have a capacity which is ideally unlimited. Again, the reliability. One of the most important aspects of cloud computing is that services needs to be always available and reliable. So unlike desktop computing, where an application can crashes because their disk could be discontinued, could be destroyed for some reason. We could have some corrupted data. This is something that typically cloud computing doesn't happen. Also because there is a constant backupping of data, and if an issue is encountered, the cloud computing the cloud computing provider is quite able to elastically move to a different version of the same application and then reestablishing the correct functionality of the system. Again, I already mentioned it, so it's possible to easily collaborate with a group of people. We can share a document, we can put this document in a folder, and the folder is shared with a group of people. Is independent of the device, so I can access the document from a smartphone. Of course, it's not so convenient to write down a Word document with a smartphone, but we can do it. Or I can do it with my desktop system. So a change that I made, of course, from my computer, this is immediately visible to everybody. And a good software as a service system enables also to collaborate at the same time in the same document. So that means two or more people can write on the same Word document, for instance, at the same time. And we are able to see, the modification in real time. This conceptually seems easy, but think about, the version control of a source code where we have also conflict, And sometimes, it happens that we commit a new piece of software, a snippet, and then we see that there is a conflict because in the same lines, some other developer wrote some line, and then the system doesn't know how to resolve the conflict. It's more or less the same approach, but cloud computing is able to do it immediately and in an easy way, and this is really transparent for us. Of course, there are disadvantages. It's not that cloud computing is the panacea of everything. The most important thing is that we need to be connected. Cloud computing is, of course, over internet. So we need a constant internet connection to use a cloud computing service. Not only, a constant internet connection, but let me say also a good internet connection. Because according to the kind of service that we want to use, we need a low speed connection or a high speed connection. Let me make an example. If I have just to read the emails, the client, the browser, for instance, with which I use Gmail or Microsoft Outlook, is just downloading text, probably some image, if there is an attachment in the email, so image or some document. Of course, this doesn't require, massive downloading of data. But Netflix is a cloud provider. It's a software as a service, like Disney Plus, Amazon Prime. They provide a streaming service. Spotify provides a streaming service, different streaming. One is just video, the other one is music. Of course, providing a video streaming service, mostly when this is provided in 4K, it needs a good connection. Okay. Otherwise, we cannot guarantee to have the 4K visualization of this thing. So the bandwidth is really important, and that's why also even in all the cities we are changing now the network infrastructure, and we have the optical fiber more or less everywhere. So the cloud, drive also this kind of change in our cities. Features may be limited. Features may be limited because the cloud provider has different service model in terms of business. Typically we have some free resources that we use without any kind of bill approach. But if we want extended features and functionalities, we pay for this. Again, the same example I did before. We had 15 gigabytes of space for Google Drive, but if we want more, we have to pay. We have a Google Doc suite with, of course, more or less all the features that needs to a common user. But if we want some advanced features that are present in, for instance, Microsoft Office, we need to pay, and then we need to unlock this kind of features. So the Microsoft Office 365 free version is not the same, of course, of the Microsoft Office 365 version, premium version, where we pay. Cloud computing can be slow, okay? Because I mean, even with a fast connection, web-based application can send time and be slower to be accessed by our desktop PC. So everything, I mean, about the program like interface, the documents sent back, I mean, and forth data from the computer that we use to the computers in the cloud. So we have a constant, I mean, exchanging of data and information, like we are doing now. I mean, we are using a cloud service like Zoom. I'm sending them in my audio and video streaming. You are downloading, you are adding video streaming. Right now, our exchange of data is going up. And sometimes could be that if for some reason the connection is not, I mean, good in that moment, the service is not discontinued. The service is that delayed. Could be that you see the voice, you hear the voice delayed. Could be that you see the image of my camera like stuck, or that you don't see the screen that I'm sharing. Then the other issue that typically I mean, scares everybody is about security. Data, of course, could not be secure, but in terms of what? In terms of the fact that data are typically stored, we don't know where. Data are not stored mandatorily in Europe, typically. I mean, not at the beginning, at least. Now, Europe is trying to regulate this. But I mean, Amazon is a USA provider, for instance, and most of the data centers, of course, are in USA. So typically, when we use a Amazon service, could be that we move the traffic to USA. Of course, I mean, today we have the GDPR, mostly after the Cambridge Analytica issue that we experienced with again the USA election some year ago. And with the GDPR, the idea is that GDPR is a European regulation. The point is that, I mean, data needs to stay in Europe, so where they are created. That's why the big player, mostly, so Amazon, Google, and Microsoft, they are building data centers, entire data center, or just cache data center in our countries. One of the most important region of, I mean, near to Italy, for instance, is the Frankfurt one. So in Frankfurt, there is one of the bigger region of Amazon AWS in Europe. Just to make another example, in Italy, then in Milan, Amazon built a cache data center where we just, I mean, where they just cache the network of the entire country of Italy. So that means the request will go first to the cache data center. If there are no data there, then it will go to the Frankfurt. Stored, I mean, data could be lost. This is something that with a good provider, I mean, almost never happens, but it's a risk. I mean, data are not in our own. We don't have data really in our disk. So could be that there is some physical error in the data centers providers, cloud providers, and then we could risk to lose the data. I mean, it's not a secret that sometimes, I mean, there were also unprevented access of data that were, I mean, stolen and were used to be sold. For instance, the credentials of the bank account. Okay, it sometimes happens, unfortunately, and that's why I mean security is one of the main issue behind the cloud. Cloud computing then means depending on others, means depending on the cloud. Okay, so if we build a business using a cloud provider like Google, IBM, Oracle, Amazon, Microsoft, without the help of that companies, we cannot have our business. So we have to accept that we depend on other technologies. Security, of course, it's a big issue to be maintained, and also, I mean, access policy is a big issue to be maintained, and this is typically something that we deal with when, I mean, the cloud provider sells the services solution. We have different deployment models. Cloud could be public, off-site and remote. It describes cloud computing where resources are dynamically provided on demand with self-service bases over the internet. Could be that there are 30 parties providers who bills for utility computing basis. And typically, I mean, Amazon, Google, and Microsoft are I mean, provider of the public cloud. Cloud could be also provided in a private environment, so it's the first step of a corporation prior, no? Prior to adopt a public cloud initiative. Because in a private cloud, I mean, the organization manages the entire infrastructure. That's why I mean they discovered I mean the advantage of virtualization. So virtualizing hardware and then serve users remotely. Cloud could be also hybrid. So that means it's done, part of the resources are on site. This is typically called on premise in an enterprise environment, or off site, so public cloud. So it takes the advantage of both. And this is typically what I mean companies prefer to adapt because they can maintain some business logic in a private environment and then I mean providing other facilities on a public. The other important topic could be cloud federation. Cloud federation means that multiple organizations or several organizations with similar requirements and infrastructure decide to be part of a big cluster. So they are part of a larger cloud where each, anyway, organization is the proprietary of that resources and infrastructure. So it's like a model to share resources and saying that I'm managing like cloud solution in Messina, just to make an example. But then, I mean, my resources are not enough to serve, I mean, the amount of requests that I'm receiving. And then I use, because I have this agreement of federation, the resources of another organization. So that means the services is not running in my cloud, but is running in the cloud of the other organization, but logically this is still one single cloud for the okay, let me now switch to something different. Let me discuss about the evolution um, of cloud computing, because today really cloud computing is often associated with different terms. Let me start from here. With different terms. Okay, one of these terms is fog computing. The other one is edge computing. Let's understand, I mean, the difference between cloud, fog, and edge. And today we have also the model of the cloud to edge computing, which is also called the computing continuum, where I mean we try to put the continuity of computation between the cloud resource, the fog resource, and the edge resource. So the fog resource was typically built because there was the need to move the computation needed to the data source. That's why I mean the trend of I mean of cloud was to move all the data that were generated over the cloud in order to be processed. This, I mean, built also the technology that today is now like big data. So we have, I mean, a really huge amount of data that are created from our devices. We typically wear also the devices like smartphones, we have smart glasses, we have smart watches. All of them, I mean, generates data. A smartphone generates data from the social networks, generate data from the applications that we use, generate data from, the browsing of the surfing of the internet. All these data are typically, in the traditional approach, sent over the cloud. Inside the cloud, there is the storage as a service, where we, of course, store the data. But there is also, I mean, the computation as a service, where we compute with our models, algorithms, anyway, general application, I mean, and we process the data in order to provide the service to the client. One of the most common application in that sense is analytics. So analytics of data that are created from a statistical point of view, but then later also from a machine learning point of view, it's something that was like an outcome of big data and cloud computing. What is the issue? The issue is that, we are really generating too much data now. And the network infrastructure is, I mean, is congestioning quite fastly. So that means the migration of this data to the cloud is becoming a bottleneck for our network infrastructure. Sometimes data are also quite big because when we just film a video of children, just for example, and then we want store them in a cloud, this, I mean, according to the quality of the camera, could be some megabytes, sometimes could be some gigabytes. So the cloud computing model needed a restyling. So that's why when the solution, the cloud computing solution, try to move next to the data source. The other reason is that some application needs to have a reply from the service and the computation, which is done in near real time or real time. This is something that with cloud computing cannot be done because, of course, there is again a network in the middle, so there is a latency that needs to be considered. A latency, so is the amount of time from which we make the request from the client and we get the response from the server, considering the fact that the cloud has also to compute that to make some processment on the data. So some kind of application like inference on of models in the cloud cannot be done in something like near real time. This is then a second reason why cloud computing paradigm try to move into next to the data source. And still, I mean, the reason why this was possible is because the devices that generates data today are not anyway, let me say, stupid anymore. They are not, they don't lack resources. A smartphone today is quite able to make a good processment. Other kind of devices are used like edge devices. Let me mention, for instance, the Raspberry. Let me mention the Jetson series of NVIDIA. There are, devices like the Jetson Orin that provides a quite good computation environment, and this is an edge device. Of course, there are different costs from a Raspberry to a Jetson Orin, but these are devices, that could be considered like small clouds next to the data source. Fog was built to manage, the proximity in terms mostly of networking. There was the need to facilitate the introduction of new technologies like the Internet of Things and the creation of these connected devices, and then fog enabled, a smart connection between the Internet of Things and the cloud computing. Typically, networking today is quite smart as well. There are software-defined networks. Software-defined networks are virtual networks that are created on a network infrastructure. These are still pieces of software. These softwares can be managed still by a cloud provider. Softwares can be created, elastically, and still on demand. So you have a pool of Internet of Things. They are part of my network. Then a virtual network is created, and this is a reason why we can maintain a good level of security, or we can maintain a good level of quality of service. So that network could reduce the latency, could manage the pooling of resources. The goal at the end is giving to the user an experience which is a good experience, not an experience where the application can fail. Examples that took advantage from the fog computing, of course, are phones, wearable devices for health monitoring, for instance, connected vehicles, augmented realities, and so on. The fog architecture, includes security, scalability, programmability, the Rust, reliability, availability, and serviceability, hierarchy, agility, and so on. The other approach is the edge computing. Edge computing, pushes really the application inside the devices that generate data. Edge computing tries to replicate fragments of information, across distributed networks of web services, and tries to replicate like a small cloud facility inside this kind of devices. Typically, edge computing, uses peer-to-peer peer-to-peer models or mesh network models. Edge computing introduces a level of self-healing, so autonomic computing. So the approach is to try avoiding something which is centralized, so that not always is is available. So edge computing could be a good companion of the cloud computing, and sometimes also a replacement. In environment where internet connection could be that is not always available, like in extreme zone. Let's think about let's make an example: the North Pole, or some scenario with natural disasters. Internet connection could be not available. So that means even if we generate data, because we have sensors in the North Pole, we have sensors in the environment that experienced a natural disaster, we cannot move this data to the cloud if the connection is broken. It could be that with an earthquake, the network infrastructure could broke. Okay, so that's why deploying edge computing, near to that areas, could replace, in this case, the utilization of the cloud. So the computation could be made inside these devices, so called edge devices. Edge devices are, of course, typically really small compared to the cloud. A Raspberry, of course, can never be compared with a full data center with GPUs and so on. That's why typically edge computing needs to build clusters, needs to have multiple edge devices. that can, I mean, share the resources, can anyway make a kind of cloud model next to the source. Edge computing today is a model that is going also with the same business model of cloud. So it's going to be provided as well using the pay-per-use mode. And of course, there are anyway certain limitations that we have to consider, because not all the applications could run inside an edge environment. Still, let's thinking about a pool of smartphones, a pool of Raspberries, or also Jetson Nano. If we have this kind of devices, we cannot train a large language models. Okay, it needs too much memory space. It needs too much time. It needs too much time in terms of computation. That still, I mean, is not possible to have a successful training in this kind of devices. At least not with the traditional approach that we use today. Of course, I mean, the research is going ahead, trying to resolve also this issue. That's why edge computing is here to work, I mean, like a standalone application, but mostly this is a companion of the cloud. And in order to be a good companion, this is why, I mean, we today try to talk about computing continuum. What I mean now with computing continuum? As we said, the computation could be done on the edge, but could be done also in the cloud. We can make like a policy saying that before we try to compute on the edge, computing on the edge has the advantage, as I say, to maintain lower the latency, to maintain, I mean, lower the congestion of the network. And something that I didn't mention, if I don't need to send the data from the data source to the cloud, I still maintain my data privacy with a good quality of service. No? Because if my data are sensible and I send it to the cloud, of course, this could be a risk. The risk could be in the migration of the data, in the storage of the data, in the usage of the data. But if data never leave, I mean, the location where they were created, I mean, the privacy is maintained. So we could have like a policy saying, okay, let's start making the computation there over the edge. At the edge, as we say, it is limited. So that means we try to have a scalability inside these devices, but they have limited resources. That's why we could say, okay, we cannot continue the computation on the edge. We need the help of a cloud resources. And that means we make something that is called offloading of the computation. So that means we migrate the computation from the edge directly to the cloud. Of course, in this case, we have to move not only the computation, but also the data where we compute, on which we make the processing. I mean, it's something that anyway we have to do if we want to have a result for that problem. Otherwise, I mean, we cannot complete the process. Okay, I mean, edge computing then was it's quite, I mean, disrupting right now in the cloud model. So really, conferences, but researchers, academia are really moving to edge computing because it's the new trend today for the computation. And I mean, also artificial intelligence is trying to move on edge devices. Alexa today, for instance, doesn't do an edge computation because it uses the cloud to make the inference of and to make the speech recognition and so on. But I mean, there is some complaint mostly about these devices. But in the future, we could have some Alexa-like device where the model will be installed for the inference. I mean, installed inside this edge device. It means this device, which is a virtual assistant, could be disconnected by internet. Okay, and be, able to serve, the user, even if with, of course, limited capacities. If we are disconnected, of course, we cannot access, all the resources and knowledge which is available online, but we can still maintain this kind of services. So mostly for privacy, for latency, network congestion, we are trying to move the computation next to the users, so next to the resource. How was possible to have this kind of flexibility? This is like just a overview of microservices, and then I will mention more during the other module that will start in a while. We do it with the microservice architecture, which is in contraposition with the monolithic one. So at the beginning, applications were built like huge applications, where even if there were different pieces of software that could be just, not, decoupled between each other, the application was just one. And this is the example of the desktop application. So if we have just to update one line of code inside a desktop application, we have to re-update the entire desktop application. Microservices try to split, where is possible, the application in multiple applications. Okay? That at the end they compete, let's say they collaborate to have one single solution. But this is much more flexible. Each microservice is much smaller than the monolith. If we have to update a piece of software which is inside one microservice, we can still maintain the other microservice active and available for the users. Let's make an example. An e-commerce website has multiple microservices, where each service could be dedicated for the catalog, is a microservice. One could be dedicated only for the review, is another microservice. One could be dedicated for the storage, is another microservice. So each of them is, they have different features. They can evolve differently within each other. Different teams can work on these microservices without, interfering with the other. And still, if we need to migrate this microservice from one machine, so from one virtual machine to the other virtual machine, we do it in a while, because this microservice is quite small in terms of size, and then we can migrate in another location. Or again, if the microservice is in the edge, and then we want to migrate in the cloud, with the microservice, we can do it. With the monolith, we can. Okay, cloud computing, I already mentioned this kind of technologies, but after the cloud computing, many technologies took advantage. In 2014, Internet of Things took advantage of this, because there was the need to disseminate internet-connected devices all around the world. Also, to monitor ourselves with, for instance, some smartwatch. But then we need to collect this data. The cloud was the model that helped us to collect the data and then to visualize, the analytics behind this data. Then, data itself, the insight of the data itself, that was a big trend mostly for digital marketing. So data were generated, in a vast amount. So all the big data challenges were born over the cloud computing. The velocity of the creation of data, the vastity of the data, the veracity of this data, because these data are also different. Data could be structured or unstructured. Data could be just text data or multimedia. Data could be small or could be big. So everything about the capturage, the storage, analysis, data curation, transformation, sharing, visualization, querying of data. Everything, I mean, was built just after the cloud computing. So the cloud computing today is becoming, I mean, really the standard, the baseline to have this kind of technologies. Okay, I mean, and let me conclude this part and then I move to the next module. Just mention, I mean, what artificial intelligence is also today. Because, I mean, artificial intelligence, of course, is here since more than 50 years, but today, artificial intelligence, as I said at the beginning, just to close the discussion, moved to the cloud. OpenAI was quite smart to move large language model to the cloud, making them ubiquitous, available from anywhere, any place, with any device. I can access my ChatGPT profile with my computer, with my smartphone, and tomorrow we can do it by voice with our smartwatch. I mean, it's not something that it's so far away. So cloud computing is becoming today also the baseline technology to disseminate artificial intelligence. So that's why, I mean, the artificial intelligence community is trying to discuss with the distributed system community in order to both providing AI solution and enabling, I mean, a distributed fashion of computation. Okay, let me now move to the other presentation. Do we need Professor Peters to make some break, or I can go ahead? I guess the break is in 1 hour. Okay.
I propose that, first of all, I don't know if there are any
Yeah,
questions.
of course, if there are questions.
There is one on the chat.
Excuse me, can I ask a question?
Tell me.
Sure. After
Uh,
we finish the question, we can have just a 2-minute break, and
no.
then you continue, Lorenzo. But please
Okay.
try to stick to the schedule, okay?
Yeah, sure.
Yeah, I was just wondering, in the schedule there's like an introduction to Docker and Kubernetes, so I was wondering when are we gonna hear about, those?
I mean, just now. I will start with microservices, which is important for containers.
Okay. All right.
Then I will discuss about containers and Docker. And
No,
then
because I had a few questions about about Docker. So
Sorry, you're going to hear about this soon, and then you have your questions, okay?
yeah.
okay,
It's
that's perfect. That's perfect. I'll deactivate my audio.
okay.
Any other question? Please voice up your questions. Don't write them on chat.
Can you hear me?
Sure.
Yeah.
Yeah, I have just a small question about the accelerator in the edge. Do you think that we can have some GPUs or other type of accelerator in edge nodes?
I mean, it's already available. NVIDIA is providing, of course, GPUs that cannot be the GPUs that we have in data centers, but there are small GPUs in devices like the Jetson series, so the Jetson Nano or the Jetson Orin. That means, I mean, it's possible to have an hardware acceleration in terms of training, for instance, but I mean, in terms of everything could be done like matrix computation, matrix calculation. And this kind of devices, I mean, helps to have an hardware acceleration. Of course, the Raspberry device doesn't do it, but if you think about the Raspberry device, was born for something different. It's like any a really IoT device, a teeny one that today is trying to run quickly, let's say, to try to meet the artificial intelligence community, but it's another kind of device. If you want to see for something that has, let's say, hardware acceleration, looks for NVIDIA and the Jetson devices.
Thank you very much.
You're welcome.
Lorenzo, I have a question. Is there really any difference between edge and fog computing?
Well, it's it's a discussion that there is also in the community, because at the beginning, after the cloud, the idea was to create the fog, so to have something that anyway was mostly related to the networking. So fog today in the cloud fog edge scenario, it's something mostly related to the network. Also, the computation is a network computation. So what is necessary to allow devices to be inside the network, to have an overlay network, some software-defined network, but not just for processing data, for example. If they are data still for networking. Okay? So fog is something that in the community it's often seen like a network-like layer. While edge computing is instead like really a small replication of a cloud, but next to the user. That's why fog is something that today we don't see much more. The trend is to have the cloud edge IoT. That's why cloud computing often is a synonym. Cloud computing continuum is a synonym of cloud edge IoT. Because day by day, even the IoT devices, and I mean the microcontrollers, they are becoming also quite powerful. Now we can do also some inference with microcontrollers, and there are also applications where some small neural network is trained inside the microcontroller. They cannot really be devices that probably we will use in production in the near future. But the trend is to talk about more about IoT, so cloud edge IoT, than cloud fog.
Lorenzo, I propose we have just then maybe 1 minute break and then you continue because we are already behind schedule, okay?
Okay.